Hi, everyone. Welcome to another episode of the Haskell Study Group. I'm your host, Ram Vedam with Atlanta Functional Programming. Today, we're going to be discussing the topic of functors. I know all of you have been looking forward to this section of our exploration of the language. I sure have. Um, Leading up to monads. Its culmination is going to be up to monads. Last week we talked about monoids and semigroups, which are fundamental type classes available in Haskell for your when designing, especially your types. You can leverage those to create algebras that are essentially associative. Their operations would be associative, binary associative to be more specific, and they will have some sort of identity. And last week, when we discussed type classes like semigroups and monoids, I brought up the topic that the book discussed on this notion of algebras, and actually designing types with pertaining to a particular algebra, and kind of gave an introduction based on my understanding of what the book was talking about in terms of um, how one might actually go and implement or create instances of this algebra, specifically the algebras for semigroups and monoids. Before we get started on actually talking and exploring functors today, I thought I'd expand a little bit on what I was talking about last week, and you will see more of it actually on this week's episode. This particular chapter, which we're only covering the first half, really. We actually a little bit less than the first half because there's quite a bit of information regarding functors that we need to discuss. The one thing that it brought up that I think I kind of agreed with was the notion of understanding each of these algebras being more powerful than the last, and what it means to actually create an algebra. And more importantly, for those of us who are day-to-day programmers, writing code and actually trying to get features done, writing software, it's often an important question to ask what all this abstraction is going to be mean for us in terms of maintainable software and building up an architecture that we can actually evolve as time goes on. Features are becoming more and more um, required and necessary to implement for our software to actually go out to end users. And I think I have a bit of an answer to that based on my reading of this initial um, chapter, and just doing some general explorations and on the last couple of weeks on some of the type classes that Haskell provides, and some of the algebras um, that Haskell provides. The first thing to note is, what is the difference? What kind of, and I'll kind of write this down for folks to see this, is what constitutes an algebra versus just being a type class in Haskell. Because as I mentioned last time, the notion of type classes is very fundamental to Haskell, and it is necessary to genericize a lot of common operations, common patterns, in which algebras actually also require you to do. It allows you to, abstract some sort of common pattern and create a type class or an interface for that set of operations or common pattern that you're types. When you're designing your types and having them adhere to these interfaces with these type classes, you have to go and implement those operations with respect to your type, so they respect the common patterns that you were actually trying to document in that type class. All right. I know I'm speaking in some abstract terms here right now, but just bear with me. And when we get started on functors, it'll become very clear. And you can rewatch the semigroups and monoids talk and discussion from last week if you want to go back and review some of that. If some of what I'm saying is starting to make a little bit more sense. Abstracting out the common pattern is very much the first step to creating a algebra, all right? That's the set of common operations that make up the algebra is important. That's what you need to think about. But a secondary thing that's important is, and this is something we've kind of alluded to last week when we talked about semigroups and monoids, but I didn't make it explicit, really clear last week when we were talking about it, is that types that implement these operations must follow some laws, all right, to preserve the actual essence of these operations. This is a very important point, okay? Preserve operations. You could think of it like their essence or their definitions to preserve their formal definitions. All right, it's probably a better way of saying it. This is a very important point to realize. It's not just the common operations, all right? If we were just talking about common operations making up an algebra, which the type class certainly allows you to create, this kind of feature is available in um, many other programming languages, all right? Take your pick what programming language you're actually going to be talking about, and this is there's some way of genericizing a common operations into an interface so you can actually implement it. So like in Java you have your standard interfaces that you can go and implement, or if you want to have default methods you can create some public abstract class, right? What makes Haskell special is it recognized not only that you want to be able to make these common operations so you can create generic functions, all right, it first separated that interface from any sort of types. All right, there's no expectation that you need a higher object hierarchy of some sort to actually go and create um, a implementation of a particular type class. All right, that's all implicit. That's number one. But another more important point is that it behind the scenes takes a very disciplined approach to verifying and expecting that when you are implementing a particular instance of a type class, that certain operations, um, uh, and at least the implementation of the instances that it provides, to be more specific, for certain type classes, it m- took a disciplined approach to actually go and make sure that those types class instances respect certain laws so that the formal definitions of the operations that make up the algebra, and more importantly the algebra itself, is actually preserved and intact. All right, that's something that I don't believe is built into the type checker. The second part about implementing operations that follow laws um, is not built into the Haskell type checker. This is something that you, the type designer, who's implementing a type class instance or who's implementing an instance of a particular algebra, which expects its operations to follow some laws. It is you, the type designer, that is responsible to make sure that when you implement it, you are following those laws. All right. And we'll talk about that today. We'll see examples of that when we're talking about broken functors and types. But this is I think the overarching theme of what we're going to be talking about the next, you know, at least couple of discussions. All right. One final thing that I want to kind of bring up here is all of these algebras, once you properly respect the laws and implement them, the rules of compositionality um, kind of fall out of them being kind of all preserved. All right, and we start with functors, but this the stuff that we talk about with respect to algebras is equally applicable to what we talked about last week, like I said, to semigroups and monoids, as well as what we will eventually be talking about when we discuss applicatives and monads. This wasn't these two particular points and this notion of algebra design and actually implementing an algebra for a type isn't clearly expressed, in my opinion, in the book. But it is something that I kind of understood, and it is something that if there are folks, hell, if the authors are watching this and they recognize that this is I'm mistaken, by all means, come talk. I would love to have you on. It'll be a great discussion. Um, but it is something that I think uh, I've at least have gained an understanding of based on reading the Haskell book as well as reading other Haskell resources online. So this is something that I think we need to at least bring about and kind of define here today. Before we actually dive right into specifics on functors, um, I thought it's important to note generally uh, what the functor type class kind of recognizes. A lot of folks who've seen functors, and I think this is the best way of doing this is showing the functor type class itself. Um, it is actually a pretty simple um, type class. Okay, at least with respect to its what is necessary to define it. Okay, and but at its heart, it's actually very, very, very at least from my what I've been reading the last few days and trying to understand, it's actually a lot more involved than the simplicity of its interface. Functors actually are stuff that we've used in already in many in earlier episodes. We've used a functor when we talked about lists. Okay, you recall that a few weeks ago when we did our discussion on lists itself, we introduced that you can actually run fmap on a list, and it will actually the it will return a list for you, a new list for you. And we can actually see this when we run, +1 on, the standard, um, just a simple finite list. All right. But what does this mean? What exactly is the functor doing? All right. What is the big deal about this? We've seen this, when we use map too as well. Why what makes its the functor type class so special? And the thing um, and the reason why I'm showing you the list one to kind of illustrate this is functors are basically generalizations of this kind of idea of mapping over a structure and applying a function to elements of a structure. It generalizes it to the fact that to an operation that could map over values inside of a particular structure and preserve the original structure that was given as an argument. All right, this is what this signature means. What it's attempting to do is essentially guarantee that for a given structure that was passed into fmap in a given function that's taking values from that structure, um, you're creating essentially like a new structure, okay, or preserving the structure that was provided and just modifying the internals of it. And since we're talking about a functional programming language here, and we know that we have immutable variables, what we're really doing is we're creating a new instance of the structure with all the stuff transformed, right? With all the underlying values representing that structure, well, being members of that structure, mapping to the actual function that's provided. And this is what we're seeing here in this example with map versus fmap. All right. What we're doing is that we're creating, you could almost think of this result being a new structure that matches what the original structure that was passed in, and every value that's kind of being constructed in this essentially being having the function applied to it and its result being inserted into the actual resulting structure. All right, this is the basic idea of what a functor does. Okay, The functor generalization of this means that it needs to obviously um, uh, require you to, specify for your type how fmap is defined. And that's the kind of purpose of today's discussion. We're going to talk about what fmap means. Because again, as you can see by the signature here, fmap is the minimal implementation in order to become an instance of Functor, that Functor type class. All right, you don't actually have to implement both. Um, as you can see here, this particular thing is a notation for actually using um, functors as a shorthand. All right, you don't have to. It's an infix operator for the functor type class, so you can use this in place of fmap if you so choose. Um, and we'll see examples of actually using this when we get to it. Functors, as I said before, just like applicatives and monads, monoids, and semigroups, are all implemented with this Haskell type class. But again, because just because it's a type class doesn't make it an algebra. There are certain laws that you need to actually go and adhere to when you are implementing your particular functor itself. All right. So I think it would be uh, kind of prudent first to kind of show some examples of the differences of fmap versus map, since obviously since we brought up the fact that you could do fmap and map on the same thing with lists and they're giving you the same result. What exactly is the functor is going to buy you? This functor generalization, um, it becomes clear when you try to supposedly apply map to an either type like just one. All right, because as you can see here, when we attempt to do that, this maybe type being passed into the map, because maybe, remember, maybe is just either just or none. Okay, again, if we look at maybe, we could see the inference structure nothing or or just a, and the fact that maybe it's itself a implementation of functor, we can actually go ahead and use fmap on top of this, but we can't actually use map because of the fact that map is defined differently. All right, so this error that you're getting, if you read it, it actually tells you exactly what the problem is, which is that it's expecting a list of of some type, and it actually got a maybe integer. Okay, and we could see that if we actually go and look at the type signature of map. Right, map is actually expecting you giving it some sort of on a function, all right, a list, explicitly a list of type A, and it's going to give you a list of type B. All right. Map does not allow you to just pass in anything, but fmap does, because fmap is defined as this generic operation that's built into the functor type class. And again, as long as there's an instance defined for the functor type class, boom, you have the ability to actually go and use fmap, the fmap operation. It's registered. It'll just do a lookup, find the type that you're trying to use, and use the implementation that's provided for that instance. This is how the kind of the machinery all kind of works. Okay. So, this is just nothing more than us revisiting type classes again, because this is all about the lookups and stuff like that. We haven't even discussed functors, or fmap itself. And to discuss fmap and how it's a generalization of mapping over something uh, that preserves the structure, we need to first introduce you to the laws of being a functor. All right, the functor laws. All right, this is has defined in the Haskell book. All right, in section um in in the section 16.5. I know I'm kind of uh, uh, for folks who are following in the order of the book that is talking about, I'm kind of jumping around and putting it in a different order. But there's a reason for this because I feel like just doing the experimentation and then talking a little bit more about um, FMAP until we talk about and then bring up the types is I think it's going in a different order. It's like you attempting to use something and not understanding what what it's all about. So I think having at least a basic understanding of the laws that are going to be involved will allow us going through some of the stuff that's discussed earlier. Um, it'll become extremely clear when we go through it. Okay. So what are these laws that we are talking about? Well, the first thing is that it needs to have some sort of identity, right? What is that identity? Basically, the idea is if you try to fmap ID on some operation, it's going to be same as passing that. Sorry, if you're fmapping an ID on some sort of you know structure, all right, whether it be a list or container or or maybe type or whatever, it's going to be the same as passing in it directly to the identity function. All right, it will not change the underlying type. It will not change the underlying structure. It will not change anything. And we could see this if we go and pass ID to say hello, and if we go ahead and pass ID to hello, we'll see that we'll get the same notion. Well, does this work for everything? So if we do ID to fmap5, we could also see that the ID uh, uh, 1 to 5 will give us the same answer. If we try even the just type that we did earlier, we could see that it will get to be just 1. If you pass in ID just 1, you'll get just 1 too as well. So this is consistent. All right, you have to make sure that when you are passing in the identity function and your structure to fmap, your implementation should make sure that identity is always returned to being the same thing as if you're passing in the identity operator. All right, this is the first law. All right, the second law is the notion of compositionality. All right, this is a very important law that we can discuss, and this here is basically the following. All right, if you are using fmap on the composition of two functions, it's the same as just calling fmap of f and composing it with fmap of g. All right, that's basically it. Okay, we'll see this as an example. Again, we're going to go and use, obviously, um, uh, our trustee list here. If we try and call, let's say that we're trying to increment something that has been doubled, all right, and we pass in 1 5. Okay, see, obviously, we're going to first call double on the argument, which will double it. So it's 2 times 1 is 2 plus 1 is 3. So this is all kind of working what we're doing. Now, this should be the same as if we did f plus 1 dot fmap of times 2 $sign 1.5. Okay, remember the $sign is mainly there so that you can remove a set of parentheses. So if you want to see exactly the same thing, you do dollar plus 1 dot fmap times 2 and then do 1. You get the same answer there. So the point of that composition thing is um, we want to make sure that the the application of the functions that you're applying the structure to are going to happen in the same exact way. There's no, again, modification of the underlying structure. It's not going to change any underlying um, uh, property of what's being passed in. All right. If it does that, it's called a broken functor. All right. If compositionality does not work for your functor instance, you have a broken functor and you have to go and fix it. Okay. This is one of those first things that people are like, well, I thought you just, when I first was looking at functors, I thought it will just do things on my own, and now it's becoming. I realized that as the type designer, I have to make sure that these laws, identities preserved. I have to do that. That's my responsibility. The type checker can't do that for me. It's not smart enough to actually do that. It just knows that there's some sort of instance available for the type class, which means it is of this instance. That's about the best it could do for inferencing. But then this is a runtime issue. This is an issue that for preservation, the law preservation is based on what's being passed in at runtime. And, making sure that those rules are preserved is entirely up to you, the designer. Which brings us to the third law, which is a very important law, which I was kind of bringing up several times, but I didn't explicitly call out on it, and that is preserving structure. All right. What do I mean by preserving structure? Okay. We've just talked about lists. Lists is a very important one, and it's probably the most obvious one where you could see structure preservation because the structure that was passed in as a list, the result is actually returned in the list. The only difference is the functions that that you passed in has the first argument that you want to apply, that you want to transform every value in that list was actually called for every value in that list, and its result was stored into the resulting object. But the actual structure of the list is technically there, all right? It is still a list. We didn't make it into another data type, all right? The result of this type here is still a list, right? So if we do fmap $1, sorry, +1 dot fmap times 2, 1, 5, and you look at the type of the result, you'll see that this is going to be resulting in list of B, which is what we were expecting. All right. If we try to do this with, say, a just clause, all right, you'll see that it'll just create a maybe because we passed in a maybe. We passed in a maybe, we're going to get a maybe back. All right. Whatever the actual structure that you provided, the actual result of the transformation is going to still be that's an instance of that structure, all right, of that underlying ADT or maybe type that you're using. That type constructor is going to stay the same. This is something that's extremely important because if you don't follow this, just like the fact that compositionality not being followed creates a broken functor, you've broken your functor if you don't follow structure preservation. All right, this is a a important point when you're talking about algebras. All right, algebras basically have these disciplined laws that your type designer as a type designer you have to make sure that you respect in order for the type class instance to actually work. And we'll see examples when we go through the uh, um, when we go through the functor examples where this can break down and this cannot break down. But first, let's go back to um, the functor definition here. Okay. And let's talk about it just a little bit. First thing the astute reader is probably looking at when they're seeing this in the REPL is the fact that the that F is actually provided in the type class definition, all right, and it's actually represented in the signature of fmap as well as the signature of the infix operator. Okay, F is going to be of the same type in all those places. It's going to be the same instance. To be more specific, it's going to be the same kind. Okay, as you can see here explicitly in the signature, when we are dealing with a functor, we're dealing with essentially a higher kind of type. All right, we're going to be when we're creating this. This is where the structure preservation things comes in again. You are dealing F itself. In order for F to be available to do some sort of functor, it must accept some sort of type argument so it can construct itself and become a fully realized type or a kind star. Remember, star arrow star means that the type hasn't been fully realized. It's still parametrically polymorphic. When you provide a concrete type to it, which is of kind star, it's going to go ahead and realize that type and create a a a concrete version of the underlying structured type that you are trying to instantiate. Um, the reason why this is important is because you might end up there's an example that where you might end up you know having to what's it you're going to have to deal with the actual the type realization and not understanding that F itself needs to be a higher kind of type is going to throw you off when you're designing your own functors. Let's see an actual example of this because this is probably going to happen. This was a good one that I thought we should discuss from the book. This is in um, uh, reference page 626 of the book, right? That I thought it was very useful to discuss. Um, you might have something called fix me, please, right? And this will take in either fix me or please. And we will we could just go and do that. And then we could go and describe, or we can even change this, to other things. The point is you have let's say you have a sum type where you aren't passing in. It's not a parametrically polymorphic type. Okay, so you could see here if I just load this here before we actually create the functor instance. Okay, and we do a type on fix me. Sorry, inf kind on fix me please. Sorry. You can see that fix me please is a fully realized type. Now, if we go and now try to define a functor on this fully realized type, and we then define, fmap, and let's just say fmap is um, uh, just some error, all right? Where we're calling, it won't compile. We're basically going to say that it's going to cause some issues here. All right. If we try and load this into our REPL, you'll see that we'll get the following error. The type checker recognized that we're trying to instantiate a type class which expects the type that we are providing to be a higher kinded type. But the type that we provided, because it doesn't take anything, and on the left-hand side, remember we have type constructors and data constructors. It's recognizing it not as a higher kind of type, but a fully realized type, and it's just going to say, okay, sorry, this is not a higher kind of type. It violates the type constraints that's required for the functor type instance to be created, and we can't actually instantiate this. So how do we actually fix this? Well, one way of fixing this obviously is providing on one side a type here. Now you can't just, create a type in the type constructor and not use it, okay? So if you try and do this, all right, it's going to cause it won't cause any issues, but when you try to define fmap, it's it, it the not using the actual type that's being passed in won't allow you to implement fmap correctly. It's going to create, again, a broken functor. Okay. So ideally, what you'd want to do is actually go in and use it. Okay, let's say that we have fix me as being a type constant, and then we use the type constructor here. Now we can actually go ahead and define fmap. Okay, instead of doing this, we can actually go in and say, okay, if we end up getting fmap with the general fix me, it's going to be nothing. But if we go in and if we pass in some f on please of x, we're just going to create price of f of x, which brings me to the one feature that I think that Haskell has that really makes it quite easy to implement functors here because it unwraps on the left hand side. Okay, um, our type argument from the underlying structure, we're able to easily define this as being as an equation, right? It's using pattern matching to ultimately say, okay, we found a plus type. This second rule is going to apply. Let's extract from the PLS data constructor that we just the data constructor that got the underlying value. All right, and that's going to be bound to the variable x, and then let's just apply f2x before constructing a new version of PLS. All right. This is pattern matching at work. Again, pattern matching to the rescue. It is really a feature in Haskell that you will use a lot and you'll come to love, especially when you're starting to implement these algebras, because it makes it very simple and clear what you're trying to actually go and do. And of course, there are other languages that implement some form of pattern matching that you can actually go and use that's very similar to Haskell. But there are pluses and minuses on using those other features from this. But for this functor piece especially, it becomes extremely clear that you could tell that fmap of f of some structure of a is going to return some structure of f of a. The function signature, it bleeds out from this definition. You can actually see what the function signature is actually doing here. So now you can actually go in and use this. So we could just say fmap +1 on +1, and you'll see that'll create +2. We can actually see if we go and create sorry, not I on fmap. If we do I on functor, you can see that we actually have our in instance safe at the top here. We can actually see that our functor has been registered correctly, and since we can actually use it, we can actually clear it up. And if we go ahead and call +1 on fix me, you'll see it'll just return. All right, it won't do anything. Okay. Um, so why did this actually kind of work? What exactly is uh uh the uh the beauty of this this functor? Because this is kind of interesting. We have this type constant. So if it has at least one type constant or two type constants that they're ignored, like again, like I said, we can actually certainly do this what we had before. If we had this as being our definition, even though we passed in an A, we could do fmap plus equals plus, and this is kind of worthless, but it'll compile because we passed in a type. Thing is let's see what happens when we try to pass in plus. Right? It's going to create fmap of plus. Let's if we do this, fix me. All right, and then if we do uh type t of fmap +1, you can see that here. Oh, sorry. I have an underscore here. You can see that this is going to actually give us a default because the +1 operator expects a numeric type. The only thing that the type checker can do is say, well, I don't know what you're generating here because this is a type constant, but I do know that whatever type that you are passing in, it should actually preserve to be numeric because +1, the addition operator, specifically now we're using it as an increment operator, an increment function requires an integer in order for a numeric in order for it to actually fully apply. So this is particularly interesting. But we can actually look at something even more interesting, which is if we look at the type of the dollar operating, something becomes very clear. If we look at this versus our dollar operator that we use, all right, this is the less than dollar operator and the dollar operator are two very different things, but they are actually giving you a very similar signature. A functor, because again, we're mapping over some sort of structure that's preserving some laws, is actually nothing more than function application. It is, we are, uh, and and that's why when you're trying to create a functor on a type constant, all right, which is what these guys are, you can't just simply make this as a enumerated type, all right? Because then at that point you're just, defining a function that you're trying to map on. You can't. What makes a functor more advantageous is it could take the type information of the underlying structure. All right, the actual values, they represent the type of the underlying values that the structure is actually using, and it will leverage that to actually go in and make sure that when it's doing function application, not only is the structure preserved, but also the values actually match the operator that you're trying to apply. All right, sorry, the values actually match the type input of the function that you're trying to apply to. All right, I'm going to pause here for just a second to see if that makes sense.
Makes perfect sense to me.
All right, give me just 1 second. There is some weird hi, let me see this. There is give me just 1 second here. We just received a comment about some spam that's clearing. It's not clearing out. There we go. Sorry about that. One of the folks who are watching the live stream, please uh uh I apologize for some of the spam chats that are coming on. One of the curses of having a public live stream is that anyone can join, and at the same time, these spam bots can actually go and throw a bunch of junk onto the live chat. So feel free to let me know if you see that again, and I will clear it up as we go along. Are there any other questions or comments? Just wait just 1 minute here for the rest of the chat to catch up. Okay, so we've seen actually this is our first functor here. Obviously, it's a pretty useless functor just because of the fact that it's not doing much, but it kind of, I hope, gives you the idea of what exactly is useful, especially when you are starting to now talk about this particular case here. right? And in fact, this implementation that we're seeing here with a type constructor that's taking in a type, but only one of the data constructors leveraging that type is what enables actually is what allows us to fmap over types like say maybe. All right, maybe the reason remember what is maybe? Maybe is nothing more than um, nothing or just a. It's exactly the same thing here, right? So the fact that we are um, uh, attempting to map over something that may be nothing, we have this type constant here, which could be nothing in the case of maybe, or it could be just some sort of data constructor of some name, all right, which is the same as just. All right. So I think this is pretty neat. This simple example shows you that you can take in some sort of type and you could define a set of rules that essentially preserves um, that the structure of it and still apply a function to the underlying value that the data constructor actually wraps. And but we haven't actually proved that this particular thing is a full function yet, have we? Sorry, a full functor, have we? Let's go through the rules again. We have ID, we have identity, we have compositionality, and we've already seen structure preservation because the fact that I can do this and pass in, sorry, I have to go and reload this. So my apologies. Okay, and if I go and run this, we could see that we can actually we're preserving the structure. We passed in a fix me please instance, and we're returning based on another fix me please. All right, so please one is a fix me please, and now please two is also a fix me please. So we can see that they're all of the same type information. But we haven't checked the other two, identity and compositionality. Well, identity should be obvious because, again, by this rule that we see here, um, we're applying ID directly to the underlying value. But let's see that. Okay, so let's pass in please one. Okay, we got it. So is please one going to give us the same here? Yeah. Okay, so we've now preserved identity. What about compositionality? Let's try again with numbers, let's go ahead and, pass in um, fmap of our plus our increment times our double. All right, just for lack of a better example, we can see this. That we're good with the left hand side of the rule. All right. What about the right hand side? Well, yeah, that's pretty obvious that we can actually go ahead and do that. We'll do plus one dot fmap 2 1. That works. And remember, for folks who are more accustomed to seeing this will also work. Okay. So we've preserved identity, we've preserved compositionality, we've preserved structured. The functor laws are actually all preserved. Therefore, this is actually a valid functor. All right. But let's see one example of an invalid functor. All right, we've actually attempted to create an invalid functor earlier with the type constants, but we haven't actually seen an invalid functor just yet. But before we do that, let me talk about one specific thing. Actually, I encourage you guys to read on this a little bit more. I'm just going to briefly mention it. This fact that functor has a higher kind of type is actually a a natural progression of an improvement that was made in Haskell. So historically, there was versions of Haskell that didn't actually have this feature, but uh, they they changed that. But I'm going to let you guys read some of that history later on. I'm just briefly mentioning it here because if you're one of those folks that have to use older versions of Haskell, you may have to go and look into how those older versions of Haskell deal with defining functors for higher kinded types, because I don't believe there are ways to do that for older versions. So I'm going to safely assume you're using a much more recent, like greater than 5, all right, in terms of version number, all right. Um, and if that is the case, this new notation that we're discussing should work for you, all right. But I'll let you deal with reading through that particular thing, all right. So let's talk through um, a broken version of a functor. All right. And to do this, let's create another type. All right. This is going to be a sum type. Again, let's call it foo of A. All right. And it contains a var or baz of A or what's it. No. And again, this is going to have the EQ implementation and a show implementation auto-generated for us. Okay, let's load this guy up. Right now, obviously, if we see this, you can just simply take a look at the example that was shown here and say, oh, we could just implement the instance of the functor here the same way. Okay, you might think, oh yeah, let's go do this. Instance functor foo where, and you might go ahead and blindly do this, bar equals bar fmap baz. Let's do what's it. Let's put everything in the same notion here. You don't have to necessarily put it in this rule, but it's better to do this because, again, remember, wildcards are given precedence over actual complete function signatures. Complete functions with arguments. And if we provide, obviously, baz with A, okay, this is a perfectly functioning, valid functor, all right? That preserves everything that we saw earlier, all right? We load this, all this is kind of working, and then we could just go ahead now and call fmap on ID on baz of 1, and we'll see that we'll get baz of 1. But let's say we take these same 5 lines, all right, and we create a broken version of this. What do I mean by broken? All right, again, it has to not validate. A broken functor is one that looks correct, but does not. It it violates one of the 3 laws that we just presented here. All right. So let's say that if we provided function here, what's it, and instead of apply a function to what's it, and we instead of returning what's it, we return bar. Okay, because both of these are type constants here, so we can actually do this. What's it doesn't take in a type argument, otherwise we can use baz to actually go and construct itself. All right, this looks correct, right? This right here, this will work, and honestly, it will actually load. Oh, sorry. Let me do this. As we're defining the same type instance. I forgot that's one of the rules that we can't violate, and that is a functor. Every type class can only have one unique instance. I gotta score 1 for the type checker there, but in this case, with this broken functor, this will actually load. All right, this this will load, but we call fmap id on bar. Remember, identity has to be preserved in order for it to be a valid functor. If we call fmap id on bar, good. If we pass fmap id on what's it though, we get bar. Right? Clearly, this violates the law of identity. Right? This is not going to um, work if we do, you know, um, id of actually, let's do fmap of id. Yeah, fmap of id on bar, id on bar. This actually is true, but if we do fmap of id on what's it equaling the id on um, uh, the id of bar, this should return false, but this is actually going to return true. This is a violation. All right. Because this is a violation, okay, this will actually be incorrect. In fact, we gotta this we if we actually completely do this right and say this is a real broken functor. All right, we only have a partially broken in case one case is actually, but if we actually go and flip these arguments around, all right, because we swapped them, this really becomes more broken, right? Because if we now call id on bar, we get false. If we do id on what's it, we get false. Both are actually incorrect. If the only thing that actually will work is if we do id on baz1 equals id of baz1. So this may look like a functioning functor, but this is a broken functor. All right, this is a clearly broken functor. All right, and it's immensely broken in this case, right? The way to fix it obviously is to correctly correct it out, and make it what we had earlier. So if we do this, simply uncomment this now will fix all that. And now if we do this, we got that. If we actually check ID on all three of these, we have our sum type all properly identity preserved, and you could check the other two to actually make sure that composition and the other things are all working. All right. The point is the laws is what is not actually enforced by the Haskell type checker. All right. But the laws are the one that you need to actually follow in order for your type class instances to be correct uh, applications of the algebra. More importantly, it means that if you follow the laws and implement the operations while preserving the laws, your type is closed under that algebra. Right? This is a formal way of saying it. It is it you can actually it preserves these properties and therefore it is closed under it. All right. Um, this comes from at least I learned it, if I remember correctly. I learned it when I learned modern algebra. I learned it from abstract algebra, and I think it was adopted by other mathematical fields. So using that phrase that it's closed under, it is a valid algebra or closed under certain set of operations, for this, and therefore it is a functor. That's something that you have to go and fix. And as you can see, this is not actually something that's enforced by the Haskell compiler. The rules or the laws for a given type algebra, in this case the functor algebra, it's not actually enforced at the compilation level. All right. What if you wanted something that does both? Okay, you can create you want something that actually changes value and structure. Well, you could do that all the time. You can write a function that takes in a list and returns a string. You can write a function that takes in a list and returns a monad. All right. You can write something that takes in some sort of value and then returns something else. All right. And change the underlying structure. All right. That's being passed in. The point of the having an algebra, though, is to be able to reuse functions and compose them. It's about enforcing compositionality. It's about being able to actually apply functions and transparently be able to compose them, completely oblivious to what structure we're passing in, because the structure that's being passed in is nothing more than a wrapper, a container of the underlying values upon which we're actually going to be um, operating on. Does this make sense to folks? Just gonna pause here for just
Yes.
a second.
Sorry for the sneeze.
No, that's fine. Yeah, so I'll repeat it just in case people didn't catch it because of the sneeze. But it's, you want to be able to make sure when you're dealing with functors, you're dealing with semigroups or monoids or any of the algebraic type classes, that you preserve the laws, because it's what the laws is what allows you to then compose different functions, ignore structure altogether, and be fairly confident that what's coming out at the very end, the result is going to be consistent and actually allows you to do more with it. You could chain things together in a much better fashion. All right. So we want to stick to those laws. It requires some discipline, but we want to stick to those laws so that we don't actually, um, mess things up. Composition is one big feature that we want to preserve, and those other two laws are necessary in order for composition to actually also work. All right. So um, it should just be something that you should recognize, and you should be able to with practice you should be able to guarantee that it's always there. And in fact, um, as we will see later on when we start discussing the commonly used functors and stuff, and especially when we start talking about testing, how do we test our own functions, this will become important. So I'm going to end it here. Um, I may create another. We may have an earlier on stream, a spontaneous stream, maybe sometimes this weekend to finish off the rest of this section, because I'm a little excited about going through the second half of this. But before I let you all go, we are off for the month of January. Um, uh, Unfortunately, I'm unable to um, be able to do streams for for the entire month. But we will be back in February where we'll talk about hopefully applicatives and monads, and I will hopefully be able to cover the rest of this second chapter before. Sorry, the rest of this chapter before we head out. So I'm just going to leave you all and I wish you all a happy new year. Um, feel free to, ask any questions in the comments inside this video. And, for those of you who are watching our public stream and are not spam bots, by all means, subscribe to our channel, the Atlanta Functional Programming Meetups. Mission is to promote functional programming, not only in Haskell and Common Lisp, although we are big into um, Haskell and Common Lisp, but all functional programming languages, we're interested in treating it as a dominant paradigm to actually design and develop software. Um, and we are looking for speakers. We're always looking for speakers. If you have a topic that you want to discuss, it can be in Lisp, Haskell, Scheme, OCaml, C++, C Sharp, Python, whatever language you want to talk about, and you want to talk about the functional features and stuff. By all means, give us a call. In fact, drop us a line if you want to do a comparison, a compare and contrast of features that you've done that are compared to um, FPs. We are not. We are If you have a talk idea, drop us a line. I'm available on functionalprogramming.slack. I'm usually squatting in the Lisp chat room there, talking to various folks. I'm also occasionally available in the Lisp Discord server as Bugram. Um, and I'm Bugram also on the Functional Programming Slack channel. So those of you who are um, there and are, who join us there and want to have conversations, drop me a line, give me your talk title, and we'll try to get it scheduled. Those of you who are in the Atlanta area, quick status on uh, our meetup, our physical meetup. So far, unfortunately, because of various constraints, our usual meetup place, which is in the ATDC, is still not available until um last time we checked, I think until late January or early February. So stay tuned for potentially having a small meetup there. And I hope to see you all in the physical realm at some point. I hope you all have a good evening. Have a great New Year's. Thanks for joining. Bye.